CLion, a cross-platform IDE for C and C++. Download now.
So, welcome to my presentation. Before we continue our journey on coroutines, just a few quick words about my work. We build various surgical training simulators with a focus on ophthalmology. They are best described when you tell people that their use case is analog to the classical flight simulator. Because the motivation that drives you not to crash a plane is the same motivation not to harm a patient. And it's similar in a sense. And for our simulators, users enter the virtual reality either through some of these widely known head-mounted displays or by looking into the microscope. That on the left is the first product that was developed in our company almost 20 years ago by now. We developed the entire platform. So the core of it is a physics-based simulation, which simulates various different of biological tissue. For example, there's the sclera, the white thingy, which is usually a pretty stiff material. There are various kinds of fluids around here. The vitreous body, for example, contains some actual fibers. And on this topic, we also have actual threads for placing a suture and closing the wound in the end. And on top of that, there's a haptics feedback loop, which is connected to these devices that look like roboter arms. And they have a 1000 hertz tight loop in which you have to continuously calculate the force for the next iteration. And if you drop a deadline here, it will instantly break down, and the immersion of the virtual reality will vanish completely. It will feel scratchy, even make weird noises, and it's completely unusable. So this is a really real-time critical part of the software. Same thing goes for the simulation, but on a less tight loop, on a slower loop, in fact. And yeah, on top of that, there's also these input devices are customized, so you can recognize the various hand pieces as they are used in real surgery. And then there's a lot of things going on. So these hand pieces are USB devices, so we get system events in combination to the tight physics simulation. Physics simulation already uses a lot of CPU cores and GPU cores. And yeah. And we've also have, of course, synchronization of user data, which involves network communication. So a lot of things are going on asynchronously on different timescales, and that's what initially drove my interest in coroutines and in this topic at all. So, but enough about that. Let's get back to coroutines. Just a disclaimer, this talk will contain yet another introduction to coroutines, but I think it complements very well with Phil's talk from earlier, because Phil took the bottom-up approach, and I will take the top-down approach. So maybe this round trip is exactly what you need to get the hang of coroutines once and for all. At least that's the hope. For me, it was kind of more natural to take the top-down approach, because usually you don't wake up and tell yourself, I'm going to write a coroutine today. Usually you have some use case in mind, and you need to know what what can a coroutine do for me? Is the coroutine a good fit for this use case? And I hope I can help you with this a little bit. Coroutines and sender-friend receivers have earlier were compared to iterators, and I want to draw this analogy here again because think of iterators. You're all familiar with the concept of iterators. It's kind of easy, the mental model. It's a concept that allows you to go from one element to another, from one element to another. And that's what you need to know. Probably all of you can use iterators, but none of you will know all the requirements of an iterator by heart and can hard code one of them just on the fly. Yeah, all of you would need to have to look up the specs, follow them closely, and then it would be no problem. And I think the same goes for coroutine as well. I would even argue it's even easier for coroutines because they don't have so many customization points, at least when compared to iterator. Of course, there's still an abundance of them, and we will consider all of them or most of them later on. Okay. So we know what iterators are, but what are coroutines? And for the top-down approach, I just go with Wikipedia first. And if you look up the definition on Wikipedia, it says coroutines are computer program components that allow execution to be suspended and resumed, generalizing subroutines for cooperative multitasking. That's easy to imagine. We've already seen the use cases. The typical examples are network transfer, file I/O, and we need some external resource, and the CPU is not busy in the meantime, and we don't want to burn unnecessary CPU cycles in waiting for the result, neither directly by waiting on the result or indirectly by having waiting cores that await on the result of the next one. Of course, we need to store the dependent tasks, but there's often things that other useful things that you can do in the meantime. So what the dream is kind of to achieve an efficient way of scheduling tasks, respecting the dependencies rather than distributing them randomly across OS threads. Note from the quote over there are two different key messages. One thing is the hard requirement to be suspended and resumed, and the other one is clarifies the intent for when to use them, generalizing subroutines for cooperative multitasking. And to that end, the coroutines have all these customization points to enable and facilitate that use case. So next, let's see what the standard says about coroutines. A function is a coroutine if its function body encloses a coroutine return statement, an await expression, or a yield expression. So we are kind of in a conflict here because Wikipedia told us earlier that coroutines generalize functions, and the C++ standard tells us that a coroutine is just yet another function. Of course, the C++ standard is our one and only source of truth, so we got to stick with that. But we can also admit that Wikipedia is also correct in a logical sense. It may be a function in terms of the standard, but logically it extends the concept. Not the definition, but the concept. So we can simply adopt both of the definitions. Or even better, let's also adopt the third one. This is my own definition. Slightly less formal, a coroutine is a function in which you can unlock special powers granted by the coroutine return type through the magical co-await keyword. So I hope you'll be getting a little bit familiar with this definition over the next few slides. At least it brings one message across that co-await does not imply waiting in general. So this is kind of a misnomer from a sense and gives you a wrong intuition if you stick with the word too literally. So let's have a look at the first and still only hero we got from the standard as of C++23. That's the coroutine return type standard generator. Yeah, it's here like in the movies. The first superhero that arrives at the scene is usually not the one you need, but it was the first and so far only one the committee agreed upon, even though quite a lot of controversial design decisions went into this one as well. Yeah, but the task still takes some time, but this is natural because the standard can't afford to make mistakes. It takes some time to agree upon. So the generator is meant to be used in synchronous contexts. So regarding our Wikipedia quote from earlier, it doesn't take its duties responsible. Seriously. But on the flip side, it's not too complicated and a perfect example to get one's feet wet with coroutines. Standard generator is a useful addition to ranges if you don't mind the potential heap allocation. But in practice, you can almost always avoid them if you don't move the generator itself, but use it on the fly as you see it in this example. This example is, in contrast to Phil, before I wasn't using standard exchange. This implementation of Fibonacci is actually what you get auto-completed if you type in standard generator by Copilot. And I thought I'd just stick with it. So you can try it again in your IDE. Just type in std generator and it will fill in the Fibonacci. And obviously Copilot is not as cool enough to use standard exchange. There are already some key observations we can make here. First, we are using a library facility, the standard generator. So click too early. And one interesting point here to make is we are using a library component, and we are both the caller and the callee of the library component. So we are writing the Fibonacci generator, which constructs an infinite range lazily. And we make use of it later on. That's kind of another thing we hadn't earlier. We can suspend and resume. That were the requirements listed by Wikipedia. So whenever I say one of the magic words, co-await and co-yield, I can suspend the coroutine and the next execution step will be potentially somewhere else. On a side note, I won't be distinguishing too strictly between co-yield and co-await because from a logic perspective, they are essentially the same thing. Co-yield is just yet another callback invoked on the coroutine promise type before you actually co-await on it. So don't worry about the difference here. Co-await and co-yield. Co-yield in this scenario means that I will suspend execution of this generator and return back to my caller, return the value. And this lazy evaluation is what allows you to write an infinite range at all. So there's because of course we can't construct an infinite sequence of numbers and return that to you. These are evaluated on demand in a sense. And another interesting thing is that that the coroutine return type, as you return it, so the user-facing type, composes well with the range adapters. So you can compose it with standard fuse, drop, and take, and then print several of the Fibonacci numbers, and yeah. So it's the infinite range is totally usable if you use the adapters after that. So another example. This is making use of the adapter standard ranges elements off. And this allows you to compare standard generators with other standard generators. So the composability is a really important aspect here. And it's the first point that makes it somehow clearer that what I was referring to magical powers, because this co-yield is more powerful than just returning to the caller. In fact, you can choose where to proceed next. So if you wrap a ranges type in ranges elements off, instead of returning the range itself that you got as an argument to the caller, it will step into the nested generator, pick the first value, suspend there, and return it to the caller of the outer generator. So depending on if you yield a value or a range is off, the coroutine return type or its promise type chooses where to go next. And this is somewhat hidden from you in general, but the generator makes it kind of obvious because you have to use the explicit wrapper type ranges elements off to make that happen. So this is a way you can compose the two, just yield a value, then yield a range, and yield again. So it will be as the sequence of 42, the Fibonacci's numbers, at least the first 5 of them, and then just -1. Okay, and another key observation to make is that the generators perfectly stack on top of each other. People always tell you that coroutines are stackless, but in a logical sense, they are. Have a look at the generator. It doesn't build up a stack on its own, but the facility of the generator builds that up for you. And the coroutine interface explicitly allows for that and facilitates that you can design it that way. And the next 2 examples I will show you will have the exact same feature. Yeah, and other than that, of course, you can call regular functions inside the generator and use the call stack of the calling thread in a sense. But inside of these functions, you can't co-await and co-yield. Because if you did that, these functions would turn into coroutines as well. And you need to make up rules in those functions for coroutines of their own. Instead of you await if you yield on other standard generators, the standard generators know how to compose with each other, and they will interact accordingly. But other coroutines won't compose with them. Other coroutine types won't compose. So that's an important thing to keep in mind. So another thing a coroutine is capable of, this is a more exotic thing. The coroutine return type can also sneak at the parameters you pass to your coroutine. So the standard makes use of that if you explicitly assign a standard allocator argt before your next argument. It will interpret this as the stateful allocator of the generator and will make use of it when allocating the coroutine frame. And you can test it out by using a polymorphic allocator. I often choose to use the null memory resource, which allows you to easily test for and guarantee that there is no actual heap allocation because otherwise heap allocation, because otherwise it will crash. And you can run that with Clang and see that it works. And that's kind of an interesting thing because it works in release build and not in debug build. Because in debug build, it will not omit the heap allocation and then access the null memory resource and crash. So you're free to play with that around a little. Oh, and just to mention that the first parameter is sometimes confusingly called a reference type, but it kind of acts like the value type when you omit the second parameter, which is the actual value type. If you just use standard generator of int, int will be the value type, and int refref will be the according reference type. That really makes a difference when you don't use trivial types like standard string. We will have some use case examples of that later on. So now back to our real concept. Yeah, our real intent. It was concurrency. So it's important to recognize that concurrency is in fact an everyday concept. Imagine the kitchen of a restaurant. If 2 orders of the same dish are placed at the same time, the chef won't cook one after another. Instead, they efficiently manage limited resource and time by cooking 2 servings at once in the same pot, making use of single instruction, multiple dishes, and using water that's still hot in a cache from an earlier order. They don't stare at the oven waiting for the food to be done. Instead, they switch to another task. When no orders are coming in, they may use their time to speculatively prepare ingredients for popular dishes. Parallelism is multiple chefs doing things simultaneously. I have a visualization for that. This works well if you can afford the overhead and until you get over subscription. Independent tasks, as we got them from the standard library function async in C++, based on threads, works somehow like this. Whenever a guest enters the restaurant, we hire a new chef and assign them the order, which they prepare independently of all the other chefs. To ensure fair access to limited resources, like the oven, each chef is only allowed to use the oven for a fixed time slice of 10 minutes. If a dish needs 15 minutes in the oven or more, it is taken out after 10 minutes so that another chef can use the oven. Once the slot is free again, the original dish goes back in. If the dish is finished, the chef is dismissed. That's the best we can do to give everyone fair access without knowing about the dependencies. The operating system does not know anything about the task dependencies. We don't tell it. So it assigns time slices. But on the other hand, the operating system knows when you make system calls or when you cause a page fault. So it's still a really powerful scheduler. So even though I was making a little bit fun of the OS scheduler, it's really good at its job. And if you are going to replace it with a standard system scheduler or parallel scheduler, that's a really hard task to get done efficiently. In particular, if you want to do a really fast task switching. So, with that introduction to our next example, this is our next hero on its way to standardization, maybe on C++26. The task. As I demonstrated here, it's part of standard exec. It's NVIDIA's reference implementation of senders and receivers, and it contains some extensions that are not yet ready for standardization. It kind of closely tracks the proposal, but it does not perfectly reflect the standard due to the refinement made in the process. The good news, it's fully usable right now. You can play with it, and it works with all major compilers. And even though some of the details might change, the basic ideas won't. So, again, you're computer scientists. I hear you like Fibonacci. Sorry about that. Here again, we can see the two core features I casually refer to as magic powers. For one thing, there's core wait when I wait on the tasks in when all, which gives the scheduler the opportunity to reschedule. And in the first place, in the fourth line, I guess, I core wait on an X read environment to retrieve the current scheduler. So not only we have a feature like goto that hides away from us what the next execution step is going to be, we also have a feature that is capable of reading the current environment, like accessing some globals. So we have a mixture of globals and goto, but all composed in a good way because they are bound by the rules that are made up by the coroutine return type. And it's up to the coroutine return type to make up sensible rules for that. Again, here, core wait in the first example just reads the value from the environment and instantly returns. So core wait in this case does not imply waiting. And in the next use case of core wait gives the opportunity to reschedule. But it also is not really waiting because it assigns the potential, it frees up the execution context for potential other tasks. Yeah. And not to forget, when we use the scheduler and spawn the futures, which are also tasks or senders, we can await on. and it awaits on the senders. We again demonstrate the feature of composability, which is kind of an extension of the two superpowers I refer to as globals, go-to, and composability, because every superhero needs a hidden superpower. And again, tasks can be perfectly stacked on top of each other. And again, the keywords co-weight and co-yield, or co-weight in this sense, in this scenario only, must be used to unleash the magic powers. You can't hide it in a function. Again, this makes it easier because you really highlight the points in the code where the scheduler has the opportunity to reschedule. Oh, and another point I should mention, this is based on the senders receivers proposal, which relies on a concept called structured concurrency. And this is why we have the scope here. The scope ensures that we await on our children. So it kind of makes sure that the parent outlives its children, so we can recover some stack traces, for example. And it also gets us out of trouble, as we will see in another example, because as soon as we have some different dependencies other than built up by the tree from this structure, we can really get into trouble with our forward progress guarantees. I have an example on the next slide. Here, I was trying to implement a coroutine task that spawns some other tasks, doesn't matter which, and cancels them once a fixed time period is over. And in this example, I'm being really cautious because I start the async scope, spawn a fixed number of tasks, then sleep, and after the sleep is over, I request stop on the scope, and only after that I co-await on scope on empty. This is in fact the only possibility to guarantee that the tasks will stop after the period is over, because I explicitly avoid calling co-await before requesting stop, because if I co-awaited on my own, I have no guarantee of being rescheduled again. Because the senders and receivers and the scheduler associated, the parallel scheduler associated with them, does only provide parallel forward progress guarantee and not concurrent forward progress guarantees. The forward progress guarantee is what have been discussed in an earlier talk. Concurrent forward progress is this is what we are used to from threads, but now we have only parallel forward progress, meaning that we can never rely on the coroutine ever being resumed. But this is usually what has to be expected when I have a static thread pool of only 4 threads. If I run these tasks, run until stopped, they may be so cooperative that they query the stop token if stop is requested, but none of them ever calls co-await. So if 4 of these tasks are running, I have no opportunity at all to schedule my cancellation or to reschedule my parent task. This is what happens when the dependency is not clear. If instead you just stick with structured concurrency, where the dependency graph is just a tree, you can execute them from down below, and even one thread will be able to finish up all the tasks. That's the reason why it wasn't a problem earlier when we called when we evaluated the Fibonacci sequence, even though we spawned a lot of threads, because we can simply start at the bottom, evaluate up the dependency graph, calculate all the values, and then we're done. But if we are relying on the fact that the parent task needs to be executed to stop its child tasks, there's another kind of dependencies. In this case, we can no longer start from the bottom of the tree. And we need to evaluate one of the or continue one of the coroutines in between. Okay, so this kind of works if you run it, but not quite, because you have no guarantee that the scope actually spawns these tasks. In fact, if you use, okay, this is just the mistake I was alluding to earlier. If I canceled my coroutine by waiting on a just stop, which will in fact in turn cancel the parent coroutine because my dependency was stopped, which cancels the task itself. And just as a disclaimer, this contains yet another bug we will investigating later. And this will introduce a deadlock because the tasks on top will run forever, and the core wait might on just stopped will suspend the parent coroutine, and the child tasks are running, giving the parent coroutine no chance to cancel them. So depending on how you look at it, you get either deadlock, because you get a deadlock when you look at the implementation of the thread pool. The thread pool has only 4 threads and rely on cooperative multitasking. So if none of the threads freeze the resource, and we don't make use of the all-powerful OS scheduler, we have no way to interrupting them and getting our other coroutine to work. So that's a deadlock for blocking the execution resources. Or if you see it in the other way and use the scheduler as given, you have a live lock, means you get only parallel forward progress, and which in turn means whenever I core wait, I have to account for the fact that I will probably never get resumed, and will maybe never get resumed, or just one of the tasks at any time will be resumed. So another example. This is just a toy example without any hopes of getting standardized. For one thing, because it's not that useful. Then again, it can be implemented with basically no overhead, and it has a pretty clear usage pattern. So who knows? And its last example to recognize some of the patterns. Maybe is like an optional as a coroutine. So it has several features. If I write a maybe coroutine, also if I write a coroutine using the maybe coroutine return type, I can co-await on other optionals. If the maybe I'm co-waiting on is null, it will immediately suspend the coroutine and returning back to the outermost parent and returning a null there. Same thing goes if std s2I, which converts the string to an integer, throws an error. We get an unhandled exception, and our coroutine return type implementation of the maybe swallows that and returns a null instead. So these exception handling use cases are implicitly dealt with there. And then I can compose this further on. So if I want to add integers given as strings, as maybe strings, I can evaluate the values on their own. I don't have to check for their return values, because whenever I co-await on a null type, I will suspend a coroutine, leave everything, and the suspended coroutine means to the caller that it's a null value and a null optional, and can simply omit further execution of the coroutine, which is kind of elegant in a sense. And it composes well. So in the second example, we first evaluate all the values, check if the values are in the range, and if so, we calculate the value, and otherwise we return an optional. Yeah, I refer to this as a monad because it's kind of interesting to recognize that all the monadic operations can be deduced or are deducible from a coroutine return type that allows you to, from a coroutine return type template that has here the integer argument, for example, in the first function, that allows you to co-return a value of the template parameter. This is the monadic return. And if it allows you to await on maybe of int and get an int out. Yeah, and in this case, the first function is like the fmap, because I'm awaiting on maybe, and then I evaluate a function which takes the inner argument and returns yet another value wrapped in a maybe type. And if I do another co-await, that's not visible in the second example, I can also implement a monadic bind based on that. Yeah? Oh. Sorry. Oh, damn it. Oh, no, I'm not proposing that for the standard. But in fact, I'm using my own return type, but the coroutines customization points are powerful enough to stick this on the coroutine, on the optional type itself. So you can implement coroutines for standard optional. So you could, in principle, return an optional from a function and use co-await inside of it, which would automatically make it into a coroutine. And then, but you then have to keep in mind that you co-return in the end and not use the usual return operator. I think this would be rather elegant. And the implementation is rather simple. I think it's a very good example to get started. If you click on there, you see my implementation of it, which can be easily improved. I omitted some optimization possibilities to show off another concept in this implementation, but you can make it even simpler and more efficient. And this would be one of the use cases where you don't almost always suspend in final suspend. In fact, you don't suspend if it's a null optional, and if it's an optional inside an optional, you need to take care to resume the parent of the coroutine, and so the parent optional after that. But yeah, it's kind of a nice exercise to get going. I just can encourage you to implement this on your own, or to get started with this one and implement the optimization I was referring to right now. Okay. So next up, I'm using this as an analogy here to explain the features we get from the standard. In fact, this what you see here on the left is what the compiler generates from us for us when we create a coroutine. What we saw earlier, there's a potential heap allocation when we do that. And there's no automatic delete, so I commented that out because the compiler doesn't give you that either. The compiler manages the suspend point for you. So if you call resume on the coroutine, it keeps track of where the last point was where you resumed it. And also one other interesting analogy, in the resume call you see here, I return nothing in if you call it more than 2 times, making it undefined behavior when you run over the final suspend. So, and you get undefined behavior from this implementation as well if you resume it too many times. So another thing to keep in mind is the coroutine handle, as you saw earlier, is really like a raw pointer. So you have to destroy it explicitly, and it also moves like a raw pointer. So really be aware of that. So if you move to a coroutine handle, the old handle will still be valid and not null. It will point to the same value. So if you write your own wrapper type with a coroutine handle in it, you can't default your move constructors if you want them. You explicitly have to set the move, reset the move from coroutine value. So this is one important thing to be aware of. And of course, of all the other undefined behaviors you can get there. Okay. So next up, okay, let's start with the awaitable concept. Okay, earlier people told you about the distinction between awaiter and awaitable. I'm not I won't distinguish between the two here because for one thing, I don't like the terms, and the standard itself doesn't distinguish between the two. In fact, the standard uses the word awaiter only in an example, and the final suspend and suspend, the suspend always and suspend never are also called awaitables. And I tried to look that up where the terminology awaiter and awaitable comes from, and it was maybe a blog post from Louis Baker from 2017, and I found no other references. Neither the standard nor the coroutine TS makes use of the terms awaitable and awaiter. In fact, the standard uses the terms awaitable and await expression, which is far clearer than these terms. So screw it, awaiter and awaitable are the same thing. Yeah, so I'm going to define one of them on my own. And this image is just meant as a provocation because, as I said earlier, awaiting doesn't mean waiting. So that's the wrong picture. And we kind of change our perspective. And let's assume we are the undisputed ruler of C++, and the committee would auto-accept all our proposals, and we could design coroutines as we wanted. We want to suspend and resume. What's the minimum thing we need? We need the user to provide tell us what it should do on suspend and what it should do on resume. So it's kind of natural to get the customization points await suspend and await resume. Additionally, we provide await ready, which is kind of an optimization, and it also has a different use case because it gets evaluated earlier. It gets evaluated before suspension. So it can optimize the suspension away, which is potentially costly. And it's also a different part of the machinery. So you first, it happens before a very central component of suspension. So it's kind of important to distinguish between the two. So you can, in the maybe example, you can, for example, destroy the coroutine immediately in await suspend because you are guaranteed that the coroutine is suspended. And if the coroutine is suspended, you can destroy it, but it would be undefined behavior to do so in await ready. And same thing, await resume. Note I put no except here everywhere because I'm later going to use it in final suspend. And final suspend is kind of special because final suspend is the point you reach when you reach the end of the coroutine, and it's also the point you reach when you throw after you have thrown an unhandled exception. It will also reside in final suspend, and after an unhandled exception, you really don't want to throw another exception. That's why you have to put no except on at least await ready and await resume on every awaitable that is planned to be used on final suspend. And to account for this use case, I just put these values here. And in fact, you're better off putting them here anyway, because it's even await suspend is kind of a mixed use case, because you don't really know if you want to do it in the context of the coroutine or do it in the context of the caller throwing the exception. And await suspend is kind of somewhere in between. The standard defines it because await suspend will throw the exception to the caller, because await suspend, if it fails, it means that the suspension hasn't succeeded. So it will resume the coroutine after suspension and throw the exception, which is kind of a weird corner case you shouldn't get into. So nevertheless. Then what you can do is, in our coroutine return type, co-await on any of the awaitables. So the examples we had already. So co-await, we are sure of that. If you await on this, we suspend always means that the control flow returns back to the caller of the coroutine return type. And when we co-await on foo or any other struct, we don't know what's going to happen next. In the standard task example, for instance, we pass control over to the scheduler and don't know which coroutine task is executed next. So it's completely up to the scheduler. It could also suspend never, so just ignore it. Also just not suspend, just continue with the execution, or suspend and drop out of the coroutine and return to its caller. That's kind of an important point to get, because if we define the awaitables, I tell you what to do on suspend and resume, but we also need the context. The scope is really important here, because if I tell you suspend always, what does it mean? Where do I go next? What do I suspend? And this is why you need the two different types: the return type, which associates the scope, and the awaitable, which decides on what to do on the specific suspension or on the specific core wait call. Then there are several other customization points you saw earlier. So initial suspend, final suspend, these are the regular, so these are the usual suspects you get out of C++, because what do you want to do on startup, on end, on finalization? That's kind of the analogy to constructor, destructor. And unhandled exception, I was referring to that earlier, return void in this example, and the constructor of the coroutine return type. And optionally, we can define these await transforms, so we don't have to co-await on the awaitables themselves, but have the context provide the awaitables for us. Is what the feature the context provides for us anyway for initial suspend and final suspend. In this case, it generates the awaitables here implicitly, and it also can implicitly generates, the compiler implicitly generates the core weight on these awaitables. But for custom points, we have to define the await transform. And this is what the other this use case makes use of. And yeah, and we could also use like the generator, define yield value and return the awaitable there. And for core weighting, I have to define the transform. And one interesting thing is I can do await transform equals 0, so delete it explicitly, which would yield to the which give you the result that you can't await on any other type inside your coroutine. So, for example, the standard generator, for example, does that. So, if you write core await inside a standard generator, it will simply give you a compiler error. And one thing, the coroutine return type, or the creation of a coroutine is really similar in a sense to a lambda function. And that's why people tell you often not to pass reference types to coroutines. But the same goes for lambdas. You shouldn't, people don't tell you to never pass references in lambda captures. You just need to make sure that the references outlive the lifetime of the lambda itself. So, and the same thing goes for here. So in this case, it's not undefined behavior because we don't actually make use of this parameter inside the function. So it's fine to use a reference here, but there are also plenty of use cases where you can reference parameters, use reference parameters. In general, you should think of the parameters to the coroutine as like the capture of the lambda, because it's like the creation of the return type, which can be invoked later. And this is similar to a lambda, but the lambda you usually call only in a stateless fashion. You call multiple times and it doesn't record the state information. And the coroutine return, coroutine is kind of the same thing, but it manages internal state. So now let's get into some actual debugging examples. Oh, that took me quite a while. So my first example is, I'm using pre-recorded screenshots here. And usually I tend to confuse myself a lot if I do live debugging. That's why I used a pre-recorded video on CPP Online. Turned out you can mess that up as well. So I'm back to slides. I hope this will work out better. Yet another type which is embarrassingly easy to write. It's this thing Wikipedia told us. It's a suspendable subroutine. That's why I call it this way, which has basically no features other than that you can suspend and resume it. So inside this coroutine, it manages its lifetime also, and you can do nothing except for suspend always if you want to continue on later, or just return the result. So, for example, in the first line, we co-return, use the suspendable subroutine like a regular subroutine or function. And in the second example, we evaluate the result, potentially throw some exceptions, suspend for no good reason so that the user has to call us again, and return the result afterwards. Again, a suspendable subroutine is the wrapper type, and multiply by 2 or multiply by 2, but suspend first are the coroutines, just like the standard told us. So these are the functions that contain the keywords co-return, co-await, or in this case, only co-await and co-return. Okay, just let's get into it. Next step. So, and then I just put on regular breakpoints in all of the customization points. So the first thing, this is what's going to get called is get return object, which obviously constructs our wrapper type. So again, as in Phil's example from earlier, the wrapper type is the type of our own. We define this interface. This interface is for our use case. It can return value for Peter, or it may do whatever. In our case, I pretend to be a regular function, so I provide operators, parentheses. In initial suspend and in final suspend, we suspend always. So we are a lazy subroutine. And in the return value, I place the value in my variant result, which maybe seen later. So after I constructed the return type, I'm immediately call initial suspend, because that's what the initial suspend is for, and then get back into main. Now, the optional result when I use the call operator leads me to a function of my wrapper type, and in this case, I look at the result and make sure that it's check if it's already available, if the coroutine has already been, if the suspendable subroutine has already been evaluated. If not, which is kind of indicated here that the variant holds the alternative monostate, if not, I will just resume the coroutine. I check for the fact if the handle is null. So I resume the coroutines once, which leads me to the body of the coroutine. So it evaluates coroutine 2 times x. Co-return means that I call return value. I forward the value inside my variant into my variant, which is now stored inside the promise type of my wrapper type that my wrapper type holds onto. And after co-return, the natural point is I reach the end. Co-return implies that I reach the end of the coroutine, I immediately call for final suspend, means that I suspend always in this case. And then I get the result. Similar thing happens when I do it with a suspend call. First get return object, initial suspend, go back to our caller. The caller calls us again. We run into our initial next manual suspend point. And when I suspend, when I reach this point, the function, the customization points of our awaitable are evaluated. So first await ready, then the coroutine suspends. We call awaits suspend, which does nothing in this case, and return to our caller. Note that await resume hasn't been called yet. We will get back to our caller. Await resume will be called only when the coroutine is resumed after that. Okay. Then when the coroutine is called a second time, here, I'm in this step. I call it a second time, so I make sure that I'm in a consistent state. The coroutine still isn't done, so I have to resume it again. And once it is resumed, I resume it, so I co-return result, reach return value, place the value there. This is going to get stored in our result variant. And now it's ready, and yeah. The next calls are going to check the pre-evaluated result and won't cause a crash. So that's okay. It's calling the suspendable subroutine multiple times after it reached the end because my wrapper type made sure of it. Then I call it again, causing an exception. And again, get return object, initial suspend, the usual stuff. Resume the coroutine, causing an unhandled exception. Now my variant, you can see the variant member down below, will store the exception pointer. And bam, I made sure that my debugger gets automatically attached when an unhandled exception is called. And this exception is called inside the call operator of my wrapper type because it implements the rethrow exception once the coroutine is evaluated from the caller side when it contains no value. So this is just to step one through a very simple working coroutine. So no bug in there, we can take it as is, but to get comfortable with it, yeah, you can step through it and you don't need too much printf debugging. So then I have two bugs considering the generator. Maybe really quickly. So this is a seemingly quick and very fancy way to concatenate several ranges. If you make use of the standard generator and the fact that all the input ranges should have the same value type or reference type, you can simply co-yield ranges elements off on the variadic pack and use fold expressions over the comma operator. Of course, you can't use fold expressions over co-yield because yield is only a unary operator. In fact, I'm not completely sure if co-yield is an operator at all. It has operator precedence, but it's not listed as an operator in a standard document. So who knows? But yeah, you can do it with the default expression with the regular comma operator, which coheres one after another. Okay, and then this works perfectly. It's just the fact that's hidden from us when you call it, because we are using ranges we pass by R-value reference, so or by universal reference, however you want to call them, and which implicitly decays to references, which causes this use case to the first use case to work out just fine, because A, B, and C outlive the reference to the concatenated range. But the second use case, where you call get numbers A, B, C, and where A, B, and C are destroyed after I access the values, will just give you an error. And I won't get into the details of debugging that, because these types of errors are immediately caught by ASYN. So I can just recommend, as always, use ASYN, and it immediately will point out the value of it. And even though it's kind of hidden away in this whole template mess, you will figure out the issue pretty soon. In fact, here's even the inline hint by Visual Studio, which tells you that it is resumed after the lifetime. So you can have a look at it. It's visible in the Godbold link, and also with the example of ASYN. It's a little bit more hidden away because I also derived the first type as a range reference, and you don't have to explicitly provide them here as the argument. And also the debug build just catches the exception. Okay. So another thing I want to show is one of the controversial design decisions that went into the generator. So I use the standard generator of standard string and print out several values as you see them here. And then I don't use the range-based for loop, but iterate over the elements individually. So I use the raw iterator and increment it once, one after another. Yeah, this leads to the following result. And the reason is, so the strings are printed out just fine, but if I read line 3 2 times, if I read the value of the iterator in line 3 2 times, the second time I will get nothing, because if I use the standard generator with standard string, the reference type will be an R-value reference, which means that the result of the iterator will be cast to an R-value reference, and once you read a string from it, you will destroy the value, which might not be what you expect. In a sense, it fulfills all the iterator requirements because it's equality preserving. So the iterators are the same, but you are not allowed to read from them twice, at least not to a standard string. And if you continue after that and increment the iterator again and again, you will also fall off the end of the coroutine. Here you get can't increment past the end iterator. So what I was doing earlier in my suspendable subroutine example, I was checking if I already reached the final suspend point, and if so, I didn't resume my coroutine and made sure in my wrapper type that I don't cause this undefined behavior. Be aware that the standard generator doesn't do that for you. Yeah, I don't think it's a real problem because you actually don't want to check on every iteration if it's still valid, because that would imply runtime costs, and it's well accepted that it's undefined behavior to iterate past the end of any range. So this is kind of no problem, but not a problem in general. But if you write your own coroutine, people won't expect that, probably. And your coroutine is not a standard coroutine, which everyone is aware of and knows of the design. So design your types in such a way that they are not so easy to get wrong, and don't push your coroutine over final suspend. So don't be that guy. Then we still have some time left to have a look at the forward progress issues I was alluding to earlier. So this is my first implementation to run a task with timeout. So I'm making use of an NVIDIA standard exec again. Here we use a thread pool of 4 threads. And started on run tasks with timeout on this scheduler. Over there, I queried the scheduler again because I didn't pass it to the function. I could have done so as well, but yeah, I'm making use again of the read environment feature. Then I construct a scope. Again, the scope is to enable or facilitate structured concurrency, making sure that the scope object is destroyed, so the child objects are destroyed, or at least awaited upon once we leave the context of the parent task object. So that's why the scope is a non-movable object. So once you placed it there, there's no way to move it to another place. Of course, you can pass handles on it by getting the appropriate tokens. But the lifetime is really managed at the place where you construct it. Then I spawn a future on the same scheduler. I explicitly start on the scheduler to make sure that it's not, in general, not to be supposed to run in place, but it might be rescheduled on another thread of the same scheduler. So that's why this explicit start on is used for. Then I call the timeout. The timeout is yet another task which awaits on just stopped after it sleeps for a duration. And after that, I'm just awaiting on another coroutine, hoping that the timeout feature will cancel the parent task, and making sure that the wrapper type finishes before the deadline reaches its end. So when I do that, the other task that's run in the loop will be evaluated again and again, never reaching the end. And which is kind of interesting, and it caught me also a little bit by surprise how fast it is to get a round trip over an unsigned integer. It just takes a second or so on my machine. if you want to await on a 64-bit integer, if it takes longer. But 32-bit integer is really fast in a sense. But nevertheless. So in this loop, I frequently await on some other tasks, see if the stop was requested, and so I explicitly provide by awaiting on another task, I explicitly provide the scheduler the opportunity to reschedule and to cancel me, in contrast to the example I've shown you earlier, where the dependent tasks ran eagerly on the thread, querying the stop token, but never actually suspending and freeing up the scheduler for other tasks. So, yeah, and the issue is, again, we have the weak forward progress guarantees, and it turns out when we query the other, when we investigate the other threads of the thread pool, they are just sleeping and never stealing the task from the other coroutine, from the other thread, because again, it respects the affinity to the thread that the task has been started upon, and if the current task has, if the current thread has only one task outstanding in its local queue, it will typically decide, no, it's just the one task I have in my queue, and after that I will take care of the next one. It's not worth stealing it from me. So it will keep it forever, and you cause a deadlock or a live lock, depending on your interpretation. Yeah. Yeah, again, I will investigate these tasks. Okay, now I will skip this example and get back to another working example. This example I'm going to skip is one that happens to work, but it's not guaranteed to either, because you can't make really sure if none of the tasks is going to free up the resource and you have only parallel forward progress guarantees, there's no way to inject your task into it to cancel it. So that's kind of a hard thing to do. If you stick with the usual approach of structured concurrency, where the dependency chains are clear and one directional, everything turns out fine, but canceling is a difficult thing to get right. For example, in particular, if it's canceled from the parent side to the child. In contrast, if you cancel a child, it propagates up to the parents and to their parents as well, and finishing up everything early as expected. But it won't work again. Okay, just to mention, I mentioned earlier that we have a bug. Also had a bug in here. The code I was showing earlier worked, for example, in a release build, but it crashes in a debug build because the current implementation of standard exec will throw an error if the coroutine is stopped and the elements of the scope have not been awaited on, which is kind of annoying in a sense, because I would need to inject an up on stopped on every co-await, catch that, then await on the scope and resume again. I'm not sure if this is going to end up in the final design, but yeah, it's not meant to be this way. In fact, the scope, when destroyed, it will, and not all of the scopes have been joined so far. It will wait, cause an implicit wait on them in a release build, and it will trigger an assertion in debug build, even when it's invoked by a just stopped. Yeah, that's why I get this error. And finally, just to have a look at our working example in the debugger where everything turned out to be fine. Where we spawn several futures, dependency chains are clear. We have our Fibonacci. I put a breakpoint there, let a few of them run, and then check the forward progress guarantees, what happens if I freeze some of the threads. So I don't have to take the C++ abstract machine seriously because I can have a debugger, I can freeze the threads whenever I want. So even though you have been initially started, you don't get any forward progress guarantees anymore. And in this case, if I just freeze one of the threads, to see if the other threads are still making progress. That's what I do here. So once they reach this point in the Fibonacci where they co-await, I will freeze 3 of them and have a look of, and we'll check what the 4th thread will be doing. So it's stuck here. Then I click on continue, and I click on pause. And it turns out, if I do that multiple times, it will never happen. The thread will never be waiting in co-await because no one's actually waiting in co-await. When the thread reaches the co-await, it means the thread becomes available to the scheduler again. And the code at the co-await point will be resumed only if there's, again, work to do. So this, when I reach the co-await and don't meet my dependencies there, I donate myself back to the scheduler, being available for other resources. And I have no thread blocking in there. And that's kind of an interesting conclusion to draw from that. And it's a different point of view, as you are used to earlier when doing the usual multi-threading. So yeah, of course, when I unfreeze the threads again, I'm just going to check if they are eventually going to make progress, and they do, and I finally get out my result. And with that, I just want to thank you for your attention and the organizers for making all of this happen.